Okay, today we're gonna do the transfer function. We just continue from what we did last week. Okay, so we're gonna do the. Okay, so here the main reason, the main objective is to find the response of the function. So we'll be given what do you call derivative, first derivative, and then we're gonna introduce Laplace. So we're going to be given a linear differential equation, and then we're going to transfer to Laplace. So we introduce Laplace. So if we have, remember I said we're making an example with a system. We did a system last week where I said we have a system, and then on the system we're going to have an input and an output. Okay, and then I said on input we're going to represent our input as RT and our output as CT for control. Okay, so here today, since we're doing the transfer function, and then we're going to be introducing the Laplace. So let's say we are given the linear differential equation as d c of t over dt. So when we introduce Laplace, we're gonna have s of cs. So this is Laplace. Okay, so when we introduce Laplace on a linear differential equation, we get this. And then if we have c of t, when we introduce Laplace, we're gonna have c of s. Okay, and then if we have the r of t, the input, we're going to have the r of s. And remember, when we're doing the Laplace, we write in capital letters. So this, we call them a transfer function. These are transfer function. Okay, so this is a transfer function. And now let's do an example when we are given the linear differential equation and we have to write it here, and we have to find a transfer function. They'll give you something like this. This is an example, d over dt plus 2ct is equals to RT. And then now here they say find transfer function. So what you're going to do here, you're going to introduce the Laplace. Okay, so remember I said the c into t over dt, we write it as as c multiplied by c of s. Okay, and then the c of t, we write it as CS, okay, with big letters, and then the RT, we're gonna write it as R and big letter S. This S, it's a Laplace operator. It shows that we're doing a Laplace. We're doing Laplace. So now when we are given this equation, what we're going to do is we're just gonna rewrite this in a Laplace form. So we're gonna have the S multiplied by C of S plus 2 multiplied by by c of s, or equals to the RT is it's r of s. So the question will say find transfer function. So to find transfer function, we'll be looking for for c over r. So transfer function, we're gonna looking for for c fraction of c and r. Okay, this is transfer function. Okay, so what we're going to do here, we can just take out the common factor of cs so that we can make c over r with the formula. So we're going to have c of s into, when we take out c here, we're going to left with s, and then when we take c here, we're going to be left with 2, and then cos to r of s. Remember, we are looking for c over r, c over r. So what we can do here, we can divide both sides by r so that we can get the fraction of c over r. So when we divide both sides by r, we're gonna have something like this. Then this one and this one's gonna cancel, and then we're gonna be left with 1. So this side we're gonna left with C over RS all equals to this S plus 1. Remember here we are left with 1, so it's going to left with what? 1 over what? S plus 2. So this is how we determine transfer function. When they say find transfer function, this is what we do. You'll be given a linear differential equation and you change it to what? To Laplace. And you're going to change it to what? To Laplace. And also sometimes they will say, okay, determine the response. They say, okay, determine the response. Let's say they want us to determine response of this equation, the one that we were given as a linear differential equation. So when they're talking about response, this is what you have to do when they say determine response. So they'll say, okay, determine response of what? Of C of t. Okay, so this one is just going back to what? To linear differential equation. So what we're going to do here, we're still going to use that equation, the C of S over R of S, which was equals to 1 over S plus 2, like this. We're still going to use that thing. So here we're going to do the inverse Laplace to get what? The C of t. When they say determine the response of C of t of the system, we're doing what? The inverse Laplace. Remember, on the first one, the transfer function, we were introducing Laplace, and now we want to go back to what? To linear differential equation. So we're gonna introduce inverse Laplace. Okay, so remember, we're looking for what? For C of t. For C of t. And then here what you have to know, will be given sometimes they'll give us a unit input. Okay, actually you'll see it on the what we call formula sheet. It's going to be given. So here on response, they'll say, okay, our RS is equal to U of t. Okay, and then we know that U of t, when we introduce Laplace, is equals to what? It's equals to 1 over S, which means therefore our R of S, it's equals to what? To 1 over S. To 1 over S, like this. So what we're going to do here, we're going to substitute wherever there's R of S, we're going to substitute with what? With 1 over S. With 1 over S. Remember, we are looking for what? We are looking for C of t. We are looking for C of t, which is linear differential equation. So here we know that C of S over R of S is equals to what? Is equals to 1 over S plus 2. And now we are given that the R of S is equals to U of t. And the U of t, when we check from the table, the Laplace table, which we see, okay, the U of t is equals to 1 over S. So now we're going to have C of S divided by 1 over S is equals to 1 over S plus 2. And then we can multiply both sides by 1 over S, okay? By 1 over S, and therefore we'll be left with C of S equals to 1 over S plus 2 multiplied by 1 over S. So we just take this 1 over S to the other side. Remember, we're looking for C of what? Of t. So here we're gonna do the inverse Laplace. So after writing the C of S as a subject of the formula, we're gonna introduce the inverse Laplace so that we can get this C of t. Okay, so we have the C of S as 1 over S plus 2 multiplied by 1 over S, like this. Okay, we were given the RS, guys, as U of t, and then when we check U of t is equals to 1 over S. Okay, and then from here we are looking for response of what? Of C of t. So to get the response of C of t, we introduce the inverse Laplace. So to get the C of t, this we call response. When they say determine the response, just know you're going to do what? The inverse Laplace. So we're going to have the inverse Laplace of what? Of 1 over S plus 2 multiplied by what? By 1 over S, like this. Okay, so now we are going to do the inverse Laplace of this. This is the multiplication, or we can write it as inverse Laplace into 1 over s plus 2, like this. Okay, so now from here we can we can solve this, the inverse Laplace of 1 over s into s plus 2. So I don't know if you guys you have that Laplace table close to you. So when we check from our table, we don't have a Laplace like this, the 1 over s into s plus 2. So what we're going to do here, we're going to do the partial fraction. So this is how we're going to solve the inverse Laplace of 1 over s into s plus 2. So we're going to have the 1 over s into s plus 2, all equals to a over s plus b over s plus 2. So this is how we do the inverse Laplace if we don't have the same the same function on the inverse Laplace on the table, on the Laplace table. We introduce we do the partial fraction. So from here, what we're going to do, we're going to solve for a and b. We're going to solve for a and b. Okay, so now moving forward to solve for a and b, we're going to multiply both sides by s plus 2. So if we multiply both sides by s into s plus 2, this side we're going to be left with 1, and then this side we're going to be left with a into s plus 2. Remember, we're multiplying both sides by what? By s into s plus 2. So if we multiply both sides by s into s plus 2, the s and s going to cancel each other, and then we'll be left with a into s plus 2, and then plus bs. S plus 2 and s plus 2 cancel each other, and then from here we can solve for a and b. So it's going to be 1 is equals to as plus 2a plus bs. Okay, and now we're going to group the s together and the one that doesn't have s together. So it's going to be 1 is equals to as plus bs plus 2a. Okay, and then what we're going to do, we're going to check on our left hand side and see if we have the value that has the coefficient of s, and we don't have it. So it's going to be the 2a is equals to 1 and as plus bs is equals to 0, because we don't have the value that matches with s. So therefore our a is going to be 1 over 2. Okay, and then here we can take out the common factor of s. It's going to be s into a plus b is equals to 0, and then we can divide both sides by s, and then it's going to be 0, and then therefore we find that our a is 1 over 2, which means our b here, b is going to be a negative 1 over 2. So after getting the answer, we're going to substitute back here, and then we find the inverse Laplace of 1 over 2s and a negative 1 over 2s plus 2. And then we're going to look at what? We're going to look on our Laplace table. I don't see my table, but for sure you are following. So this is what's going to happen. We're going to have the c of t inverse Laplace of 1 over s into s plus 2, and plus 2, and remember we say a over s plus b over s plus 2, and then we find a as 1 over 2 and b as negative 1 over 2. So what we're going to do, we're going to have the c of t equals to the inverse Laplace of a over s. Our a is 1 over 2 over s, like this, plus minus 1 over 2, we substituted back the values of a and b, over s plus 2. And now we can find the inverse Laplace of 1 over 2 1 over 2 over s. Okay, so what we're going to do here, we're going to have 1 over 2 inverse Laplace of 1 over s. So we know the inverse Laplace of 1 over s. We're going to check on our table. Here we're going to have a negative 1 over 2 inverse Laplace 1 over s plus 2. like this. So this 1 over s, the inverse Laplace of 1 over s, we can check on the table. Let me go find the table. So the inverse Laplace of 1 over s, it's 1. So here we're going to have 1 times 1 over 2, so it's going to be 1 over 2, okay? And then the inverse Laplace of 1 over s plus 2 is going to be what? Negative 1 over 2 e to the power of what? To the power of negative 2t. So this is our response. When they say determine response, this is what we do. We introduce what? The inverse Laplace. Okay, moving forward, we're going to do transitional mechanical system and rotational mechanical system transfer function. Okay, so we're going to do what? A translational mechanical system, which is what? A transfer function. So a transfer function, okay, transfer function. So here under transitional mechanical system transfer function, we are going to have 3 elements. We're gonna have 3 elements, which is mass, spring, and a damper. So we're going to have 3 elements, which is gonna be mass, a damper, we're gonna write it as Fv, and then we're also gonna have a stiffness, spring. Okay, so let's say we have a mass, okay, with a force. Let's say we have a mass like this, and then we have a force going to the right, and then we have a displacement like this. Okay, we have a displacement like this, and then now we can generate a equation of motion from this diagram. So we're gonna use the Newton's second law method, where F is equals to ma. Okay, and remember here we have a displacement. We can also write our a in terms of x. To write a in terms of x is gonna be x dot dot. So here our equation is gonna be f of t. F of t, it's equals to m x dot dot t. Okay, we are writing our acceleration in terms of x like this. This is what we call the linear differential equation. And then here, from here, we can introduce Laplace both sides. When we introduce Laplace both sides, we're gonna have the big letter F of s. Remember the s, it shows that it's it's Laplace operator. Okay, or equals to m, and then the acceleration we can write like this when we introduce Laplace both sides. So we're gonna have the m s squared, big letter x, x of s. So this is how we write when we introduce Laplace both sides on our linear equation. We're gonna have this. Okay, so we introduce Laplace both sides. So Laplace of f of t, it's f of s, and Laplace of mx dot dot, it's ms squared multiplied by what? By x of s. Okay, so this is for mass. When we're going to use this when we are asked to determine transfer function. Okay, so when we're talking about transfer function, it's Laplace all the time. Okay, so we just have to introduce Laplace both sides, and then we get this equation. And then from here, let's say we have, remember I said we have 3 elements, so we're done with the mass, and now let's do the stiffness. So let's say we have a spring, and then on that spring we have the force acting this way, and then let's say we have a displacement, like it stretches. then we're gonna have the x of t like this. And then now we all know that the formula for spring, it's what? F is equals to kx like this. Okay, so remember this one, it's in what? It's in linear differential equation. And then when we introduce Laplace both sides, we're gonna have the big letter F of s. Remember, the s represents, it shows that we're doing Laplace. It's gonna be equals to k of x of s, k multiplied by x of s. Okay, this one shows what? Laplace. And now for damper, remember I said damper, we're gonna use what? FV. So for damper, let's say we have a damper like this. And then on this damper, we have the force acting this way. Okay, and then we have a distance this way, x of t. And remember, what we call the damper, it represents the friction between what? Two surfaces. It represents friction between what? Two surfaces. So here, the formula for damper, we're gonna have f of t is equals to the damper. Remember I said the damper, we're gonna represent it with fv multiplied by the velocity x dot, okay, of t. And then when we introduce Laplace both sides, we're going to have what? Big letter F of s equals to what? F of v, since it's velocity, we're going to multiply by s x of s like this. So for damper, this is how it looks like. Okay, and then moving forward, we can make an example of this mechanical this translational mechanical transfer function. So the question will come, they'll be like, okay, we'll be given a diagram, and then they say determine transfer function of x over f of s. And then what you have to do, you have to draw the free body diagram and then do the equation of motion. After doing equation of motion, you make the x of s, the x over f, substitute the formula. So let's do an example of this transitional mechanical. Okay, so let's say we are given a diagram like this. It's connected, we have a spring connected to a wall. We also have a damper which is connected to a wall. Okay, and then this damper and the spring, it's connected to the mass like this. Okay, we have a mass, and then we also have what? We have the force F of t. Okay, and we have a displacement like this. Okay, and now they ask you to determine what? They say find the transfer function. They'll say, okay, find transfer function of what? Transfer function of x of s over f of s. So they'll give you a diagram like this, and then they'll say, okay, find the transfer function of what? Of x over f for what? For the translational mechanical system. For translational mechanical system like this. Okay, and then what you do first here, you start by drawing a free body diagram. The free body diagram is going to help you to determine what? To determine the equation of motion. Okay, the equation, so that you can get what? The transfer function of what? Of x over f. So what we're going to do, we're going to draw a free body diagram. Number one, we draw a free diagram. We have a mass. We have a mass, and then now we're going to check, okay, if we pull this force to the right, what's going to happen? When we pull this force to the right, the mass and the damper is going to oppose. Remember I said the damper, it represents the friction between two surfaces. So when we pull the mass to the right, the damper and the force is gonna oppose. So we're gonna have an arrow going to the side. This is K, and then this is FV. So FV, we're gonna use FV as what? As damper. So we're gonna start with the K. So it's gonna be K multiplied by X. So we're gonna have the force of spring opposing. So we're gonna have the K multiplied by x1 of t. Okay, and then we're also gonna have a damper. The damper is also gonna be opposing. So it's gonna be opposing going to the side. So it's gonna be FV multiplied by what? By x dot 1 of t. Okay, and then we have the force acting to the right. So we're gonna have the force acting to what? To the right, like this. Okay, so now we have our free body diagram. So when after getting the free body diagram, we're gonna use the Newton's second law, or F is equals to ma. Okay, so we're gonna use the Newton's second law. So it's gonna have we're gonna have F is equals to ma, like this. So we're gonna add all the forces that we have, and we're gonna equate it to what? To mass multiplied by what? By acceleration. So we're going to have the force acting to the left, which is the spring and the damper, and then we're gonna have the other force acting to the right, which is this force Ft. Okay, what we're going to do here, we're gonna take our left as negative and right as positive, and then bottom and top, bottom as negative and top is positive. But now we are dealing with the x-axis, so we're gonna use the left and the right. So the left one is gonna be a negative k x1 of t. Okay, and then we're also gonna have a negative f of v x dot 1 of t, and then we have another force here, which is plus f of t. Okay, all equals to m, and then we're gonna write our a as in terms of x. So we're gonna have the x dot dot t. Okay, like this. And then after writing our equation of motion, this linear differential equation, we're gonna introduce Laplace into this equation. Okay, so when we introduce Laplace, remember for stiffness, it's gonna be what? A negative k big letter x of s, okay, minus f of v. Remember, this is acceleration, so it's gonna be multiplied by what? S multiplied by big letter x of s. Okay, for damper is s. Okay, plus f of s. Okay, f of t, Laplace of f of t, it's what is f of s, all equals to m, and the Laplace of x dot dot is gonna be what? S squared big letter x of s. Okay, this is s here. This is what we have. Okay, so when after introducing the Laplace, remember we are looking for what? For x over f. So now we can make x over s subject to the formula. So what we're gonna do, we're gonna start by making f of s subject to the formula, and then we're gonna take this to the other side. So we're gonna have the ms squared x of s plus k x of s plus f of v s multiplied by x of s, like this. Okay, let's turn to the other page. So we have the f of s is equals to ms squared x of s, okay, plus k x of s plus fv s x of s, like this. So remember, we are looking for what? For x over f, like this. So what we're going to do here, we're going to take out the common factor of what? Of x s. So we're going to have f of s equals to x of s into ms squared plus fvs plus k. like this. And remember, we're looking for what? We're looking for x over f. So what we're going to do here, we can divide both sides by what? By f of s. So what we're going to do here, we're going to divide both sides by what? By f of s. And then this one and this one's going to cancel, and then we'll be left with 1 equals to this. Multiplied by what? By ms squared plus fvs plus k. And then we can divide both sides by this ms squared plus fvs plus k. So we're going to have this. This is what we're looking for. This is what we are looking for. And then we are done with the first question that we were asked. They asked us to determine what? To find the transfer function of x over f. Transfer function of x over f. That's what we do. The first thing we do is to determine the what? The free body diagram, is to draw a free body diagram. After drawing a free body diagram, we do the equation of motion. And then after equation of motion, we introduce Laplace transform. Okay, we introduce Laplace transform. After introducing Laplace transform, that's where you make the x over f substitute the formula. Okay, so moving forward, I see we have what we call test 2 preparation. We're gonna do activity from test 2 preparation. We're gonna do this activity. We're gonna do this activity. They say find is the last question, I think, on that preparation of test 2. They say find the transfer function g of s, which is equals to x3 over f of s. So here we are looking for what? For x3 over f. So for the translational what? Mechanical system shown in figure P 2.13. So here you can see we are given 3 masses. We're also given 2 stiffness. We also have what? 3 damper. Okay, so what we're going to do here, we're going to remember the first thing is to draw a free body diagram. After free body diagram, we generate the equation of motion. After getting equation of motion, we can introduce the Laplace 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 transformation. So this is what we're going to do. Let's move forward. We are given that activity, I think it's number 27 from test 2 preparation. Okay, we have this diagram like this, where we have a spring, we have a mass of 4 kg, we have a damper, and then we also have another damper here. Okay, then we have another mass of 4 kg. Okay, and then we have a spring. We have a force here, Ft. And then here we have the last mass, 4 kg. And then we have a damper here, like this. Okay, so all the dampers are 2 Newton meter. So the damper is 2. All the dampers are equals to 2, and all the springs are equals to 6, and all the masses are equals to what? To 4. And then from here we have a distance of x1, and then here we have x2, then here we have x3. Okay, so remember I said the first thing that we do here is to draw a free body diagram. So the first mass, which is connected to 6 Newton per meter, the stiffness on our left, we're going to name it M1. So this is our M1, and then this one is going to be our M2, and then this one is going to be our M3. Okay, so guys, we're doing this activity. Okay, we're doing this activity. So remember what we do first. We draw a free body diagram. So we're gonna start with the M1 and then M2 and then M3. So okay. Sorry. So now here we're gonna start with what? With M1, a free body diagram of M1. So we have this M1, and then we're gonna check. Remember, we have force going to the right. So when we pull this mass M1 to the right, what's gonna happen? This spring is gonna oppose. So we're gonna have a spring going to the left, which is gonna be Kx1. Remember, we're doing what? M1. So we have a displacement of what? Of x1. So remember, we are pulling this mass to the right, and then this mass, this spring is gonna oppose. And also the damper, while we are pulling this mass to the right, this damper is gonna, remember the damper, it represents the friction between two surfaces. So here is the surface and the object, which is mass. So even this damper is going to be opposing. So remember I said damper, we represent our damper as FV. So we're going to have this damper opposing. So we're going to be FV x1 dot. Okay, x1 dot. And then what else? Remember, this damper is between mass 1 and mass 2. So it's connected to what? To the displacement number 2. So which means while we are moving to the right, also the displacement number 2, this damper that is connected to displacement number 2, is going to move together with this mass to the what? To the right. So we're going to have another force going to the right for the damper. So it's going to be FV x2, because this damper is between M1 and M2. M1 with the displacement of x1 and M2 with the displacement of x2. So these are the forces that are acting on M1. Okay, let me show you it clear. This is what I was saying. This M4 kg, the one that on the left, the small block, when we pull it to the right, the spring is going to oppose. So it's going to go to the left. Even this damper that is connected to x1 is going to oppose. It's going to go to the left. Okay. And then also when we are pulling to the right, remember this damper is between x1 and x2. So it's going to go with x2. That's why we have another force going to the right. Okay. That's the forces that are acting on M1. Okay, so from here we can do the equation of motion. So what we do, we're gonna write the Ft is equals to ma. So it's all forces equals to mass. Okay, M1 here, A1. So we're gonna add all the forces. Remember the left one, the left forces, we take them, we're gonna use a negative sign, and the right one, we're gonna use a positive sign. So here is gonna be a negative kx1 minus fv x1 dot 1 is equals to m1. Remember a, we're gonna write it as x, so it's gonna be x1 dot. Okay, like this. And now we have the values, we can substitute. Okay, so we're going to have a minus 6x1 minus 2x1. I forgot the other force here, the fvx2. Sorry. So it's gonna be a plus fvx2. Okay, like this. fvx2 equals to m1 x1 dot 1, like this. Okay, plus, remember fv is 2 damper, and then for damper, because it's velocity, we have the s here. So it's 2s x1 2s x2 or equals to m1 x1 dot. Okay, x1 dot. Remember here it's 1 into t 1 into t, 2 into t, and then x1 into t. And after writing our equation of motion, now we can introduce what? Laplace. Oh, I am so fast. I am so fast. I was already introduced Laplace when I write the S and S here. Sorry. So here it's x1t minus 2x1t dot plus 2x2t dot. Okay, like this. Yeah, we have to write it like this. And then after here, that's where we introduce Laplace. That's where we introduce Laplace. So for stiffness, it's going to be negative 6x1 of s. And then for damper, it's going to be negative 2s x of s1 plus 2s x of 2s equals to m1 Laplace of x dot dot is going to be s squared x of s, like this. Okay, and then after here we can make we can just equate this equation to 0. So we're just gonna take this negative 6, negative 2, and then positive 2 to the other side, and then take out the common factor. So now let's move forward. So we have a negative 6x1s plus 2s x1s plus 2s x2s equals to m1 s squared x1 s, like this. And now I was saying we can take this negative 2 and 2 to the other side. This is negative, guys. Sorry. So we have m1 s squared x1 of s plus 2s x1 of s plus 2 s x2 s plus 6. This is minus, sorry, we took this to the other side, plus 6x1s, all equals to 0. And now we have the x1 and x1, so we can take out the common factor. So we're gonna have x1, and the force, I mean the mass, it was 4. It's 4. All the masses are equals to 4. So we have 4 here, we also have 4 here. Okay, so we're gonna take out the common factor of x1s. So we have x1s here, so we're gonna have s squared, and then we also have x1 here, so we're gonna have plus 2s, and then we have x1 here also plus 6 minus, we have this 2, we don't have the other dimension, so it's gonna be 2s x2, or equals to 0. So this is going to be our first equation for m1. So m1, we have the transfer function equation, okay, for m1. After here, we're going to do m2. We're going to do m2. M2 is the middle mass, okay, 4 kg. So you can see 4 kg is connected to the first damper, is also connected to the second damper here, and is also connected to what? To spring. Okay, so we're going to have the forces acting on this mass. If we pull it to the right, the damper, this damper, is gonna oppose, it's gonna go to the left. Okay, and also remember this damper is also connected to x1, so when we pull it, the x1 is gonna move with mass to the right, and then the x2 one is gonna be opposing this damper. We're talking about this damper, okay, and then the top damper is gonna move together with what? With it's gonna oppose, because we're going to pull it to the right, so this top damper is gonna also oppose. And then we have the spring is between x2 and x3, so when we pull, the x2 is going to oppose and x3 is going to go together with what? With the mass. Okay, so this is what I'm saying. The M2, the free body diagram of M2, remember we have the force F of t. okay, and then we have a spring which is between mass 2 and mass 3. So when we pull that spring to the right, x2 is going to be opposing, so we're going to have the k going to the right. We're also going to have the k going to the k x2 going to the left and k x3 going to the right. Okay, so it's in between, and also we have a damper which is between mass 1 and mass 2. So when we pull that mass to the right, the damper is gonna oppose, which is connected to mass 2, so it's gonna be FV x2 dot. Okay, and then remember it's also connected to mass 1, so mass 1 is going to go together with that mass, so it's going to be going this way, FV x1 dot. Okay, and remember we also have another damper on top there which is connected to mass 2, so that damper is going to be opposing, so we're still going to have another damper this side which is FV. We have FV again, which is x2 dot. Okay, even here it's x2 dot. Okay, FV. So we have two FVs going to the left. Okay, because we have two dampers. Okay, we have two dampers. So now our free body diagram is gonna look like this, and now we're gonna do the equation of motion. F of t is equals to ma. So we're gonna add all the forces. Okay, so we're going to start with the left side, so it's going to be a negative FV x dot 2 minus FV x2 dot, and we also have a negative k x2. Then on the side, on the right hand side, we're going to have the plus FV x1 dot, okay, plus f of t plus k x3, okay, like this, all equals to m2 x dot 2 of t. There's t here, of t, this is 3. And from here we can now substitute. Remember, all the dampers are 2 and all the springs are cos to 6 and all the masses are cos to 4. So FV, we're gonna have a minus 2 x dot 2 t minus 2 x dot 2 t minus 6 x2 plus 2 x1 dot plus f of t, okay, plus 6x3 of t equals to 4x dot dot 2, like this. Okay, and now from here we can introduce the Laplace. So we're going to have a negative 2s x of s minus 2s x of s minus 2x2, remember here is x2 of s plus 2s x of 1 of s plus f of s. Laplace of f of t is f of s plus 6x3 of s equals to 4x squared x2 of s. And from here we can take out the common factor x of 2. Okay, we can take out the common factor x of 2, and then we're gonna have f of s like this. Okay, we're gonna make f of s under the formula, so we will end up with x2 of s into, we have the 4s squared plus 4s plus 6 like this, minus 2s x1 minus 6x3s. Okay, this is our second equation. This is our second equation for what? For the second mass. And then let's do the last mass. So it's gonna be M3. Okay, M3. So this is the last mass. The last mass is connected to what? To the damper. Okay, to the damper, and it's also connected to what? To the spring. So when we pull this mass, the last mass with x3, when we pull it, the spring is gonna oppose. Remember, the spring is between x2 and x3, so the x3 one is gonna oppose, so it's gonna go to the left, and the x2 one is gonna go to the right, so it's gonna go together with the mass. And then this damper is also gonna oppose. The last damper, this one, is gonna oppose. So we're going to have the K with x3 to the left and the damper with x3 to the left, and then the K with x2 to the right for the last mass. Okay, so this is what we're going to have. So we're going to have the force of what? Of spring going to the right, left, kx3, and then we're also gonna have Fv x of 3 dot, and then on the right we're also going to have the k x of 2. And now from here we can do what? The equation of motion. F is equals to ma. So we're going to have negative k x3 minus Fv x dot 3 plus kx2, or equals to m3 x3 dot dot x3 dot dot. Okay, and now we can substitute the values. Remember, all the k's are equals to 6, and then Fv equals to 2, and then masses are equals to 4. So we're gonna have a negative 6 x3 of t minus 2 x dot 3 of t plus 6 x2 of t equals to 4. The mass is equals to 4. It's equals to 4, like this, 4 x3 of t dot dot. Okay, like this. And then now from here we can introduce the Laplace. So it's going to be 6x3s minus 2sx3 plus 6x2s is equals to 4x squared x3s. Okay, so we're going to have a negative 6x3s, okay, and then minus 2s x3s plus 6x2s, or equals to 4s squared x3s, like this. And then from here we can take out the common factor of x3. So just gonna take this other thing to the left, to the right, and then we take out the common factor. So we're gonna have the 4s squared plus 2s plus 6 minus 6x2s equals to 0. So now we have 3 equations. This is the third equation, and remember the question wants us to determine what? x3 over f of s. So we have 3 equations. So from that 3 equations, that's where we're going to determine the x3 over f of s. So let me just write the equations, and then you'll see how to determine the x3 over fs. So the first equation, it was x1 into 4s squared plus 2s plus 6 minus 6x2 equals to 0. That was the first equation. And then the second equation, it was x2 into 4s squared plus 4s plus 6 minus 2s x1 minus 6x3 all equals to f of s. This is second equation. And then the last equation was x3 into 4s squared plus 2s plus 6 minus 6 minus 6x2 all equals to 0. And then from these three equations, we're looking for what? We're looking for x3 over f of s. We are looking for this. So you just have to play around here and then get what? The fraction of x3 over f of s. So at the end, when we solve this, our x3 over f of s is going to be 3 over s into 8s cubed plus 12s squared plus 126s plus 18. Okay, plus 18. So this is the final answer is gonna look like this. Okay, I think we're gonna stop here for today, and then when we meet again, we're gonna do rotational mechanical transfer function. Here, remember, we were doing translational. Translational is just a mass, a spring, and a damper. So on a rotation, it's gonna be rotating. So you'll be given a torque instead of ft. So you'll see how this rotational works. It works the same as this translational. The different is it's rotation, just that it's rotating. We're gonna have the moment of inertia here on rotation. Okay, so